Okay, so recording is on, and then I need to show you the website. Website URL is here. So it's sites.google.com, metropolia.fi, then DSP BRS, like digital signal processing problem solving. That's the URL. All of you have also a laptop, right? Good. Do you have MATLAB on your laptop? Not yet. Okay, tomorrow you will have. Actually, you need some. Do we have MATLAB on these computers? This. Oh, no MATLAB then. Okay. Do you know any lab that has PC lab that would have MATLAB? Okay. Okay. We can take a look at if it's free. We will be using actually MATLAB to solve the problems. Oh, okay. Welcome. But okay, you should have the campus license for MATLAB. So download the your version to your own computer. It should run pretty well on almost any platform, and usually students have much the newer computers than any university. Thanks, budget cuts. Okay. Anyways, today my plan is to go through the sections 1 and 2, which is signals and systems, and basically this is really a intensive course. It means intensive work on the exercises. I have also some brief notes on the theory part, which may or may not be enough, depending how much you have been told by mathematics teachers and other teachers here. But anyways, so the signals and systems are the first 2 paragraphs. Then we go to the system responses, then FIR filters, IIR filters, finally embedded systems. I'm trying to cover 5 topics in 4 days. Since Wednesday you have something else. But today, tomorrow, Thursday and Friday, we should have time between 10 a.m. to 5 p.m. Right. That's on your calendar, I hope. I wish. Okay, first things first. I would like you to enroll to this course first. There's an enrollment link for Born-Bright 6 University of Applied Sciences. Like. URL. Yes. Sites, Google.com. I can actually write it here. google.com/metropolia.fi and then DSP BRS. Found it? And going there, you should go and click for the enrollment link. Course name. You can put there the digital signal processing or whatever is the course name in your own syllabus. It does not really matter. Course code, don't worry about that one. Only the parts which are marked as asterisks are compulsory. And why I'm collecting this information? I will enroll you into Metropolia system. So in addition to the this bond right seek credits, you will also receive Metropolia the certificate for this part. Okay. So personal information, first names, last name, day of birth. Yes, we need that one for the enrollment purpose only. And the yes, actually this, let's see this one. Metropolia US respects the privacy of the students in handling their personal information. Information provided in this e-form will be transferred to the student register of USA's. More information about the register, the GDPR kind of thingy description. So you are not going to get any spam email or anything like that from Metropolia. Not even if you want it. not by filling this form. And gender, well, although there is a selection, use either or. The other is not in the national register yet. It is next thing what they will be updating. Yeah, sure. Phone number, well, if you want to give that one, that's fine. Email address, use your favorite email address which you are using for the studies. Study email address. Preferably the one that is also in active use. Okay. Then the other ones, redirects, postal code, postal CD. I'm not going to check those. If you want to put some dummy variables there, it's up to you. Native language and nationality is actually something that we are collecting for statistic purposes. Statistics, and of course the home university. That is good information. Yeah. So fill that one, and later on at some point you will be receiving the Metropolia credits if you manage to do the exercise. Okay. Let's go through some general stuff. How does it go? So basically, there are always some lectures. Lectures are also recorded, and if the recording is good, then I will also save it for the later use. Each of these theory also is supported by slideshow. It's the Google Slides show, and then there are really nice place to look after the mistakes, go through those mistakes so you don't repeat them. Frequently appearing mistakes. There are some assessments. Okay, assessment for the Finnish part. This is actually assessment of this part. I think it's about 50% of your regular course year. But in addition, you will also get a separate certificate from Metropolia. And that's the Metropolia assessment. So you need to get at least 40% of the points, total points. And anything between 40 and 100%, the Finnish the grading scale is from 1 to 5. 5 is the best, so it's a linear scale between 1 and 5. Easy. Exercises, well, we are not going to do all of those. We'll go basically up to the 6th exercise. The first one I think we will do together. The second one I will give you just the hints how to do it, and then let's see, third one. Yeah, that will be tomorrow. That will be individual. Then 4 and 5, I can put on Thursday, and then on Friday there's the embedded systems part. Maybe something like that. We will see how far it goes. And again, frequently appearing mistakes. Scoreboard. Let's see. I do have a scoreboard. Yep. If it's okay, I can post these the grades or the puzzle grades or points in this kind of table, which has only your first name as ID. If it's okay. Of course, I need to get your consent on that one since GDPR. Then anyone opposing, give some phony name that you can recognize yourself from the list. But I think the 5 students, I think you know already each other's. Oh, right. Then the last line there. Creative Commons Attribution Non-Commercial Share Alike 4.0. Meaning that if you want to make a business by selling this one, I will send some lawyers to talk with your lawyers, see which one has a better lawyer. So for non-commercial use, just use anything what I have here. Non-commercial meaning education, mostly. Okay. Any questions about the how this course is actually managed? So this is kind of general stuff here. Okay, let's go directly to the business then. Signals. Wow. Signals. I heard that you made a nice exercise of signal generator on this box. So did it work? Excellent. At least one worked. So you basically have already some experience on making a. Let's see. How do I get it? Huh. Oh, there it is. Full. On how to generate signals, meaning the fundamentals of a sample system. So now we talk a little bit about the digital signals. So what is digital signal processing? Yada yada blah blah. But anyways, there are some parts of the digital signal processing. Usually it goes like that you have a sound source or some other signal source. Then you have some gain and fitting the small signal actually to the when we have the at the end we will have A to D converter which gives you values between 0, 0 and FF or okay, well, maybe biased, but anyways, first thing what you need to do for the signal is to have some gain, maybe also level shifting. If you have a tiny signal, you will just make it a bigger signal with level shifted to right place. Then next one is there is the anti-aliasing filter, meaning you will cut off the frequencies which are too high for the A to D converter. So it's somewhat smoother, and then you can actually digitize it. So that's how you get a real signal to A to D converter. Okay, so after sample and hold, you have digitized the or sampled the data, meaning that you have a signal which is analog in value but only at certain times. And the A to D converter actually does the quantization of those signals, so they actually are appearing only on certain bit values. Okay, so in the beginning, you need some analog filtering, analog processing. That's usually called the analog front end of ADC. So continuous time and continuous value signal. Next step is the sampled, which means that in theory that on that point the signal is still analog, but it's sampled in time, and then digital signal is discrete time and quantized value, meaning a decimal number instead of floating point number when it comes to the A to D converter. There we go. And there's a cat. Okay, so this course is mostly about the sampled signal. Only the last, or sixth paragraph, which is the embedded systems, that actually covers some things that what happens if our system is actually also discrete value, quantized value, meaning fixed point precision. But, well, nothing to worry about until Friday. So usually on this one we use the continuous time, continuous value but discrete time signals. Okay. So sampling rate is the value that tells how often you take the sample of an analog signal. These are not the greatest. Okay, at some point I will get some better. Maybe that's better. So, for example, slowly varying signal, then you just have the decide the sample rate and set the sample time accordingly, or the other way around. But usually the sample rate is the first one. And then that also says also what is the sampling interval, which is 1 over fs. On your signal generator, what was the sampling rate? One millisecond, yes. So quite low frequency signals generated. Good. Yeah, 1 millisecond, so that's 1,000 samples per second. Then there's the Shannon's theorem. You may already have heard of it. You must take at least 2 samples per original signal period. Yeah, that's it. If you take less, then basically bad things happen. Something like that. So aliasing happens. So if you have it, that the sampling interval here has been way too slow, and those points are now the red ones are the points showing where the samples were done, and that blue one is the real analog signal. You can see that actually our sampled signal looks sinusoid, but with totally wrong frequency. So we lost that information at some point. Okay. Yeah. Digital signal, also quantized in value. Okay. One important parameter there is the signal to quantization noise ratio, which tells basically what is the dynamic range of your signal. For example, on 12 bits you get about 74 decibels of quantization noise ratio, so not hi-fi quality audio. Yep. Example. So human ear, you can still hear some above 20 kilohertz signals. I'm not hearing those anymore. And neither are you after 30 years. Ha. Okay, or 10 years if you're using this headset and put too much power on them. You will lose your high frequencies first. Okay, so human ear can detect signals roughly between 20 and 20 hertz to 20 kilohertz, roughly. And you need at least 40 kilohertz sampling rate in order to sample that one. Okay, CD quality PCM. PCM is pulse code modulation, meaning that it adjusts the values for each sample point. Digitized values. 44.1 kilohertz sampling rate is a standard audio sampling rate for example, Sound Blaster and such kind of equipment. So-called CD quality. Listening music, okay. Normally sound pressure levels in range of 20 to 100 decibels. Okay, peaks are actually at 100. You shouldn't go above 80 decibels on the audio pressure on continuous or the continuous volume. So basically, you need more than 13 bits of resolution, and for easiness of storing, the CD quality PCM signal has been selected to have 16 bits resolution. That should be enough for high or CD quality audio signal. Not the professional levels. That requires 24 bits and higher sampling rate for the processing purposes mostly. Okay, couple of basic sequences. Discrete delta, meaning that it's basically integrated over time sampling time, which means that on continuous time delta you have at 0 time you have infinite value, but it still has the basically you can integrate over time and it gives you the energy of 1. This is the same thing actually. So it's basically not sampled delta, but it's well, root mean square sampled values of those well, they from minus 0.5 to 0.5 time region. Okay, but anyways, it's just a peak. Discrete Dirac delta function is useful for when you are generating, for example, some well, impulse responses. Analog systems, you must use the step function, meaning the rectangular wave, in order to find out the basically, for example, finding out the system transfer function. But in digital domain, we can use delta function. Another one, basic signals, the basic signals on discrete time system. Another one is unit step signal. You can also, of course, use that one as an input to the system and see what is the step response of the system. And now you can compare the analog and digital corresponding systems. And then there are some relations between delta and mu. Delta function is the same as the difference of the two subsequent samples of step function, and the step function is basically the oh, that's wrong. K from 0 to infinity actually. Okay. Periodic signals. Continuous time periodic signal periodicity is quite easy to find. So basically, if it's sinusoid signal, then you just basically find the place where the time, or find the time delay where the signal repeats itself. And the shortest of those is the base period. On sampled signals, it's not that straightforward. The definition is still the same, but actually on the sampled signal, you cannot use real numbers for the time. That's indexes. And unless the sinusoid or this periodic function is somehow directly related to the sampling rate, they basically this sampled signal is not periodic anymore. Usually they are not. Okay. Yeah. Yes, you can actually define the frequency periodic signals as a Fourier series. You have heard of Fourier series, right? Good. I'm not bothering you. More of the random signals. So basically, any signal that doesn't follow any systematic mathematical formula, then it's called random. There, for example, small-scale turbulence or mechanical structures of microphone. Actually, that's the wind noise in microphone. And yes, that is random. Then a couple of other random noise sources. One, which is always, there is a shot noise in electronics. So if you have current carriers are actually quantized, the one electron size or multiple electrons in some cases, but anyways, mostly just single electrons that are moving. And with a very low current, you can actually hear that one. It's like a popcorn popping, pop, 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 pop. Something like that. Then another one is Johnson noise. So actually, it's caused by the random thermal movement of charge carriers in conductors. Meaning, if you have a resistor like that, you have these carriers which are actually jumping up in and out from the resistor. Well, it produces a random voltage across the resistor, as long as you have any temperature. Okay, so at least those three random signals are always there. And of course, any signal like speech should be considered as random. Natural processes. This is probably something which has been covered in some other course. I hope. Well, honestly, I don't care if it's covered or not. Two types of distributions, either Poisson, meaning that is throwing your dice kind of thing, or flipping a coin kind of the distribution, or then with big numbers, anything follows the normally distributed random numbers. And when you make the histogram statistical analysis of the data, they usually end up being either the Poisson distribution which is left, meaning no negative values, or then a nice Gaussian shape. Then it's the anomaly distributed. This is the model. Reality might be a little bit different. Okay. When we're talking about signals, it's also important to take a look also on the cross-correlation or correlation of the signals. So the correlation measures the similarity of two signals. This has applications, for example, on the radar technology. You send a short pulse out that actually then scatters back or reflects back from the object, and then basically it's the similar amplitude what is that, signature as the pulse you sent, which means that when you then make the cross correlation of the pulse that left this transceiver and returns back, gives you information about where it actually reflected back and how big is the reflection and how far it was. We just calculate the time we took from the correlation. Autocorrelation measures the self-similarity of the signal, and actually this radar is more using the autocorrelation than cross-correlation technique. Okay, what else? Couple of things how the correlation should be calculated. If you calculate correlation of two signals directly from those formulas, it basically takes a lot multiplied calculations, but you can also do it with the large data set. You should do it on frequency space. Okay, so Fourier transform of the signal multiplied by the complex conjugate of the Fourier transformation of the other signal. That actually, if you take the inverse Fourier transformation of that will give you the cross correlation of two signals. This is poor mathematics. You don't worry about how it's done. It just works. It's a tool. Okay, there's the correlation example, acoustic radar or, well, sonar. Or depth finder on ships. They're using the correlation technique. Okay, so correlation is used to find the self-similarity or similarity of the signals. Convolution. Convolution actually gives you the tool to do some spectral phase filtering. So basically, convolution of the two signals is defined by that. Again, you don't need to usually to make those convolution calculations yourself. There are some already made packages, for example, for these. But anyhow, the filtering of any signal, linear filtering, these are bad. Any better? Okay. I really should draw them, but okay. So I don't have a picture either. No, that doesn't give any good point there too. Okay, whatever. But we will actually follow this one later on when I'm talking about the filtering. But anyways, it's based on linear convolution. If we know the impulse response of the system, then we convolute the input data with that impulse response, and then we get the output. So that's the finite impulse response filter. Impulse response, which is measured or defined by some the filter design method, basically defines the whole filter. Okay, more stuff. Signal to noise ratio. Okay, signal to noise ratio is 10 times the logarithmic 10 base clock of signal power divided by noise power. And it happens that both signal power and noise power are directly proportional to the variance. Now you got some use for variance from mathematics. It measures the power or energy, either or. Well, signal power basically is equal to variance. There's only just it's a simple, multiplied by a scaling factor or a calibration factor. Okay, but that's pretty simple to calculate. Spectrum analysis. You already had the Fourier spectrum analysis a couple of weeks ago, or last week? Yes, you did. I have heard spectrum analysis using Fourier transform. No. Oh. Yes. you know. Nice try. Okay, Fourier transform. Well, nothing. Well, there's absolutely nothing into it. It's just calculate the Fourier transformation of a signal sample, and then basically multiply it with the complex conjugate. That's a signal power spectrum. But I will show you with the MATLAB later on. Yeah, there's an example of the spectrum analysis here. This is also a nice example that, okay, when you have a analog signal, single frequency analog signal, basically the frequency, there's supposed to be only one frequency there and nothing else. But because this frequency was not exactly the multiple of this sampling rate, it means that you also get these aliasing wings there, or Gibbs effect wings, either or. But anyways, it's not periodic anymore. There's more into it than just periodicity. So when you are sampling any signal and do the spectrum analysis, the spectrum analysis is basically, it has some artifacts which are actually coming from the window. The way you cut mathematically a signal, for example, like this, is that you will multiply it with a window. With square wave window, then it basically gives you that kind of wings for the wignets for the measurement. Same as here. Have you got any radio frequency classes? Maybe. The same thing, why you don't usually send the radio frequency bursts like that. First of all, it's very expensive to make the amplifier, but on the other hand, it produces lots of the side spectrum, which is disturbing the other frequencies. So usually on radio frequency transmission, you would have an envelope which has smooth edges to suppress those down. Okay. More things about the spectrum analysis. So if you calculate the Fourier transformation, it's basically for the one single section of the data. But usually our signals are long. And for example, if you have a chirp signal with varying the frequency, meaning that the frequency depends linearly from the time. Then basically calculating one single spectrum wouldn't make much sense, since it would produce a flat spectrum. You have equal amount of power on all of those frequencies. But when you also add into the time dimension, then we are talking about spectrogram, which is a time series of spectra, meaning that if you have a sample like that, you will take the first sample here, calculate the spectrum, second sample here, third sample, fourth sample. So you cut this big sample into smaller pieces. And then show this one, each of those spectra as one column on this picture. So time goes that way, frequency goes that way, color coding is the power. There, that was the first part about signals. Let's go and maybe I should have a short break now to give you some time to install some programs. Did you take your computer with you? Oh, yes, you have. Okay, we will have a small break. You got the longer. Excellent, excellent. Thank you very much. I'm quite sure that it works. Okay. Which wasn't there? Wait a minute. Huh. Yes, it works. Good. Now I can actually turn this one a little bit more. Thank you. All right. So I will have a short break on my recording.